right yesterday? Okay, good. So it is somewhat worthwhile.
I'm gonna watch what you say.
Let's do this. I want to march through material on derivatives. Hello, Gloria. I want to march through material on derivatives, and after I do that, then I'm going to take questions on the mapping. We seem to be missing a Miley. My brain is so foggy today, I lost count midway through. 12, 13, 14, 15, 21, 24. So we're missing a Philip and a Miley and somebody else. All right. So, derivatives. We want to divide up derivatives into concept, evaluation, and using. Concept. dy dx, or f prime of x, is the instantaneous rate of change of y, or f of x, with respect to x. That's its full name that it uses when its mother is angry with it. But usually we just call it a rate of change. Understanding that it is instantaneous. What is it that makes it instantaneous? What makes it instantaneous is the definition. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. Or the alternate definition, f prime of c is the limit as x goes to c of f of x minus f of c over x minus c. What makes both of these the derivative is that it is a change in y over a change in x as the denominator goes to 0. Notice in both of these that the denominator is going to 0 here. And that's what makes it instantaneous. Geometrically, f prime of c is the slope of the line tangent to the graph of f of x at x equals c. Notice we have two things here. We have the concept of slope of tangent line, and we have a specific point of tangency that is x equals c. And if you want a concrete example of for yourself, a great one would be f of x equals x squared. F prime of x is equal to 2x using your derivative rules. And let's pick a point of tangency. How about x equals 3? F prime of 3 would be 6, meaning that at the point 3, 9, the point of tangency, then we have a tangent line with a slope of 6. Just like that. Aha! Why is it 3, 9? Because the point is defined by the function, whereas the slope of the tangent line is defined by the derivative of that function. Good question. I did that hoping somebody would ask or notice. Good. So that's concept. How do we go about evaluating these derivatives? Evaluating the derivatives is complex for students because information can come at us in different forms. One way that information can come at us is graphically. If I have a graph of f, and I wish to find the value of f prime of c, then my preferred method of choice is going to be to draw a tangent line. And find its slope the good old-fashioned way, change in y over change in x. And if you wish to label these dy and dx in honor of Mr. Leibniz, then he would be proud of you. And you can simply compute the slope as dy over dx. So our technique for graph is draw a tangent, find its slope. The related skill was, if I have a graph of f, sketch a graph of f prime. So here's a graph of f. And now I want to sketch a graph of f prime. And the basic procedure by which we did this was to find the zeros or other critical points for f prime, and then find the sign. And we accumulated that information in a number line. And that number line should be a well-labeled number line. F prime right here. We have a 0 at this point, and we have a 0 at this point because f has horizontal tangents at those points. On this side of my 0, in this region, f is increasing, f prime is positive. In between here, f is decreasing, so f prime is negative. And on this side, f is increasing, so f prime is positive again. And now I'm going to draw a smooth curve. Smooth because my original curve is smooth, right? I'm going to draw a smooth curve that is positive, negative, and then positive. Ta-da. Notice that I am not looking at the direction of f prime. I'm looking only at the sign of f prime. Is it above or is it below the axis? James, would you hit the door, please? Does everybody see here? I know that on your quizzes on this, many of you did well. A couple of you were lost. So does anybody have any questions on the process of drawing f prime? What if f has a sharp corner at x equals c? What will that look like in the derivative? Nope. It'll be a jump discontinuity. That's right. Because f prime is changing values instantaneously when it c. What if f has a vertical tangent? What will that look like in f prime? If f has a vertical tangent, what would that look like for f prime? What kind of asymptote? No, it would be vertical because f prime is infinite. So if f has a vertical tangent like so, then f prime has an infinite slope right here at x equals c. And in fact, I can tell from the slopes of tangent lines running up to that that it will be positive on both sides. So that f prime will have a vertical asymptote just like that. Does that need more explanation? It is. Oh, in other words, it's supposed to be positive everywhere. Yeah, I was a little sloppy here, wasn't I? Let me keep this above the axis. So this needs to stay above the axis and be positive. Good. Thank you. Yep. No, you were right, and I was wrong. I was fixated on what was happening right here at C. Okay, so that's graphically. What about numerically? For example, suppose I gave you a chart of values for x 0, 0.1, 0.2, 0.3, And here are some values for f of x. And I now ask you to estimate the value of f prime of 0.2. Then we're going to think of this as a slope, right? And we're going to use the smallest possible delta x that we possibly can. And the most accurate is a delta x that is on both sides of the 0.2. Here is my x equals 0.2, and I'm going to take a slope using 0.3 and 0.1. And my work looks like this. F prime of 0.2 is approximately change in y over change in x. And then I can plug in values. This gives me 1.8 minus 2.0 over 0.2, which is negative 0.2 over 0.2, which is negative 1. But honestly, usually we don't need to simplify. And so that's a numeric computation of the derivative. If I wanted just from the left or just from the right, then I would take just the x value to the left or just the x value to the right. What about analytically? Analytically is where people get pretty comfortable because we've been doing it a lot. Our big tool for analytic stuff is the derivative rules. And those you guys have been practicing with and using a whole lot, so I'm not going to go over the entire thing. I will put up a list of derivative rules on Headline. I have a study sheet that you can use to do those. Should you be able to prove any of those? Well, you should be able to prove the simpler ones. Be able to prove the ones for tangent, cotangent, secant, cosecant, and also the ones for inverse sine, inverse tangent. If you can do those 6, then you're pretty good to go as far as that goes. The one that does need a little special care and feeding is the inverse function theorem. So I'm going to take a minute to talk about that. First of all, our form which is that inverse prime of x is equal to 1 over f prime of f inverse. And the way in which we use this, let me give 2 examples of this. One was, we use this to find the derivative of the natural log of x. We set up the limit definition first, and the limit definition gave us fits. We didn't know how to simplify what we had, so we quit on that. And we said, all right, instead, let's consider the inverse function theorem. And so to use the inverse function theorem, we're going to think of this function as an inverse. That means that we need to identify the parent function that it is the inverse of. Natural log x is the inverse of what? Of e to the x, exactly. And to use the inverse function theorem, we need f prime as well. Since I have f of x, f prime is easy enough. It is also e to the x. And so, using the form of the inverse function theorem, the derivative of f inverse should be 1 over f prime of f inverse, or 1 over e to the ln x. And that simplifies because e to the ln x cancels, giving me 1 over x, which is exactly the derivative of natural log that we know of. So this is a good analytic example of how to use the inverse function theorem. What if I have a table of values in some way? For example, what if I give you I'm not very imaginative here. My f of x and my x and my f of x are going to look like this. But let's make up some numbers here for f prime. They're all pretty clearly going to be negative values, right? Because my function is a decreasing function. Let's make this negative 2, negative 0.5, negative 0.8, negative 1.3, and negative 4. Something like that. So I've got a table here. And now I ask you, what is the derivative of f inverse evaluated at x equals 4? Or f inverse prime of 4. Does everybody understand the question? Okay. And so now we appeal to the inverse function theorem to do our heavy lifting for us. We're going to say that f inverse prime of 4 is, give me the form, everybody. 1 over. And specifically of 4. I'm looking for f inverse prime of 4 and not just f inverse prime of x. So now I evaluate that inside out. I'm going to start with the inside. What is f inverse of 4? To find f inverse of 4, I go back to the place where f is 4 and ask what x solves that equation. What x solves f of x equals 4, and that's x equals 2. So I'm looking at 1 over f prime of 2. Then I go back to the table and I ask myself, what is f prime of 2? It is negative 0.5. And if my inner nerd feels so compelled, I can simplify that to negative 2. Questions on this? Because I know that the inverse function theorem was confusing to some people the first time. I'm getting a dazed silence. Does this mean that you are all totally with me, or you are all totally lost? 2 thumbs up if you're good. Okay. Good. There's no shame in asking questions. So if you have questions, please. Calculator. What can I use my calculator for? On the calculator section, there will be calculator-based questions. And you absolutely should know when to use your calculator for the calculator-based questions. What can I do with my calculator? It can graph.
Zeros.
Let's generalize that. Not just zeros. Intersection points, and when it does, what is it doing? Solving. That's right. It can solve, which includes finding zeros and intersection points. And the third thing that it can do for you? Derivatives. That's right. Yeah. It can find dy dx at a point. Okay.
Wait, is it going into the same thing as dy dx and zeros and stuff?
So what would a typical calculator kind of question look like? Well, let's see here. Let's throw this into the context of motion along a line. Let's say that I have a position s of t given by the square root of t squared plus 2 sine t. Okay. And I now ask you, what is the velocity at t equals 1? Everybody can see that this might be a typical sort of question we might want to answer, right? So how would I answer this in a calculator active session? First, I need to give the language that shows I understand the concept. What is velocity in relationship to position? It is the derivative. So my answer is first of all going to say that v of 1 is equal to s prime of 1 for ds dt. Okay? S prime of 1 is the best way to say that. Now having said that, I'm going to ask myself, how do I evaluate this derivative? I've got two options. I can take the derivative using the derivative rules by hand, or I can evaluate the derivative directly on my calculator. And so how would that go? How would that happen? If we let y1 equal the thing that I am looking for the derivative of, we do a quick double check to make sure we're in radian mode, not degree mode, because we've been in physics. And then we do second calc dy dx. And find the derivative at x equals 1. Go. Why did I say we should not find the derivative by hand here? Because you can't do it? No, you can't. It's actually a waste of time. It slows you down when you need to be able to have your time freed up to think about the thinking questions. What do you get for a second? That wasn't my question. What do you get for the derivative? What's that? 9404. Yep, that's about right. You got one? Yeah, she does get one.
Yeah, that's correct.
1.000145. She's in degree mode. She did not do a check to make sure that she was in radian mode. Everybody check, make sure you got this answer and not the 1.0001. Okay? Good. What can we do with our derivatives? First of all, motion along a line. Velocity is the derivative of position. Acceleration is the derivative of velocity. If my velocity has a positive sign, what does that tell me about the object? Object is moving to the right. That's exactly it. If my velocity is negative, that means the object is moving left. And if the velocity is 0, that tells me that the object is stopped. That's exactly right. How long is it stopped for? Instantaneously, right? And we take as our example the pen going up and down, right? Stops at the top, but only for an instant. Acceleration is more subtle. If the acceleration is positive, what does that tell me? tell me about the velocity? Yes. No, it doesn't tell me that, interestingly enough. No, it doesn't tell me that either. I could have velocity is 0 and acceleration is positive or negative. For example, at the very top, velocity is 0, but acceleration is negative 9.81. Let's take it literally as a derivative. Since acceleration is the derivative of velocity, if acceleration is positive, what has to be true about the velocity? It has to be increasing. That's right, the velocity is increasing. Does that mean the speed is also increasing? No. What do I have to have for speed to be increasing? Velocity and acceleration have to have the same signs. That's right. So if acceleration is greater than 0, velocity is increasing, but not necessarily the speed. If the velocity is negative, then an increasing velocity will mean it's getting less negative. It's moving towards 0, the speed is decreasing. If the acceleration is negative, the velocity is decreasing. And we'll just take this as a matter of definition. If velocity and acceleration have the same sign, then speed is increasing. If velocity and acceleration have opposite signs, then speed is decreasing. And there's our motion along a line. I can guarantee you some kind of motion along a line questions, so I want to make sure that you practice doing something. What else can we do with our derivatives? We can construct tangent lines. And to construct a tangent line, we need a slope, and that's going to be at c comma f of c, where c is the point of tangency, and we need a point, which is c comma f of c, where c is the point of tangency, and we need a slope, which will be f prime of c. And a typical kind of question that I might ask might be something like, find the equation of the line tangent to y equals ln x that goes through the origin. You guys remember this question from your homework, right? And so the first thing that we wanted to do to keep our head straight was to sketch a graph of our situation. We sketch a graph of y equals ln x. And we take a line through the origin that is tangent to the curve here. Do I know exactly where this line hits? I do not. What do I do about that fact? Call it a variable, that's right. This is going to be c comma f of c, or c ln c specifically, because my function is natural log. And now, what can I say about the slope of this line? I can say two things about the slope of this line. First of all, I can say, because I know 2 points, 0, comma 0 and c ln c, I can say that the slope must be equal to change in y over change in x, just like so. But also, because the line is tangent to the graph, I also know that the slope is equal to the derivative of natural log x evaluated at c, which is 1 over c. This slope is from 2 points. This slope is from f prime. Does everybody see how we're taking that information and putting it together? And now it's a matter of solving this equation. Everybody solve this equation. Yeah. Yes, sir. Lost on what?
When I was drawing the graph,
Mhm.
And then,
You're good with the graph?
yeah.
Yep.
No. Can you explain that again?
Yeah. Natural, do you know the shape of natural log? And this is it. Okay. Then I want a line that is tangent to this curve that goes through the origin. So I start at the origin and I just eyeball a line that is tangent to the curve. And there's only one way to draw that line so that it goes through the origin and is tangent to the curve. It's like that. I draw it like that or that, it's not tangent. So I draw that one line and I label that point C, L, and C because it's on the curve. Okay? And then I find its slope with 2 points. I find its slope with f prime. The slope has to equal the slope. Set them equal, and now I solve. How does my solution go? Somebody help me out here. Gloria, you got it? Uh-oh.
So Mr. Prager, what's the other pair that's on the left of the graph?
What's what?
The other that you have in brackets on the left of the graph. Left.
Oh, 0, 0, the
Oh.
origin.
Right.
Yeah, sorry about that. Yep.
How'd you put the slope as one over C?
What is f prime?
The derivative
Yes, but in this specific case, what is f prime?
for the slope,
In this specific case, what is f prime?
1 over C. Oh, okay.
Oh.
What is f prime? Or y prime, we should probably say.
Y prime is 1 over I.
1 over x. And what is our x value? It is c. Yep. We did these problems a couple times before, but I think what some of you did was you just sort of checked out because you didn't fully understand it. All right, Gloria, we need a solution here. Help me out. Give me something I can do with this equation. You know something that you can do with this equation. Oh, she can't see it. Oh, well, you should be sitting here. Not next to Philip. He's not going to hit him for you. Come, sit.
Did you find the value where L and C equals 1?
Okay. Can you see it now? Yeah. Okay. So we have ln c minus 0 over c minus 0 equals 1 over c. Can you think of anything sort of obvious that we could do to simplify that? For example, can you simplify ln c minus 0? Okay, you're not giving yourself a chance. Calm down. Everybody around you is your friend. So, think about this. ln c minus 0 is the same as what is x minus 0 the same as? Yes. So what is ln c minus 0 the same as? There you go. So you knew that. Right? Okay. So I can simplify this as ln c. On the bottom, c minus 0. Aha. And now this is still equal to 1 over c. So I have ln c over c equals 1 over c. Can you think of anything that I might do to simplify this a little bit? This is Gloria's problem. You're taking her. So I have this equation, ln c over c equals 1 over c. Can you think of anything I can do to simplify this? Why? What do I do to get that? The bottom's the same. So what can I do with that bottom in order to eliminate it? Yeah, that's right, good. And we call this strategy clearing the fractions, multiplying both sides by a common denominator. And when I do, I get ln c equals 1. That's very good. Now I just have to solve for c. How will I do that? Somebody help her out. This is the key move. What does she need to do to solve ln c equals 1? Raise e to both sides because the exponential is the inverse, and e to the 1 can be simplified as e. That's right. So we finally get our value for c. Did we answer the question? Do a quick answer test. Nope. We need the equation of the line tangent. So what information do we have here? We know that our point is e comma natural log of e. What is natural log of e? 1. So we have e comma 1. And our slope is 1 over c, or 1 over e in this particular case. So we now have a slope and we have a point. We can put it together to get y minus y1 equals slope times x minus x1. Or I could use the other point, y minus y1 equals slope times x minus x1. Both of these are exactly the same line. Question?
So why does the ln c over c should be on the slope?
Why is the slope this? Because the line goes through 2 points. One of those points is 0, 0, and one of those points is c comma ln c.
So isn't ln c over c?
It is. The slope is ln c over c. It is also 1 over c because that is the derivative of natural log of x, evaluated at c. Because my line just doesn't go through these 2 points, it is also tangent to the curve. 2 conditions, 2 different computations for the slope.
Oh, so after I got the like ln c over c, I integrated with it. So
I did not take the derivative of ln c over c. I took the derivative of my curve because I'm looking for the line tangent to this curve. And the slope of the line tangent is the derivative.
oh,
That's the concept. Yeah. I'm very emphatic on this because I've taught this 3 times. And some of you are just finally going, oh, I need to know how to do this. Cool. So hopefully, light bulb. Better? Philip is doing the right thing. He's asking these questions that need to be asked. Okay, at this time, I think we've reviewed what we need to on derivatives. We have a little bit of time if you have questions about your packet. Yes? 60 on free response. Estimate h double prime of 0. Okay, yep. All right. So we have this information given to us, like that, and we are looking for h double prime of 0. I'm going to think about it like this. H double prime of 0 should be going to either side of 0, h prime of 0.1 minus h prime of negative 0.1 over 0.1 minus negative 0.1. Thinking of the second derivative as the derivative of the derivative. Only problem is I don't have this information yet. but I can find it from the information on H given in the chart. What's that? Well, I asked you to make a chart, oh, do I give you H prime then? Oh, good. Hey, how about that? And so this is 5, 2, and 1.5, and I just plug in.